All right, like I said, welcome back. We look at performance characteristics in this video. Okay, so over here we're going to look at the average number or the expected number of customers in the system and in the queue, and the waiting time and everything as well. So let's just dive into the video. So first of all, we look at the expected number. Okay, or average number of customers in the system. We know average from probability, your probability distribution knowledge, or the random variables. Expected value should be equal to like the random variable times the probability, right? Good. Summed over all of these possible domains, right? That's okay. So we sum ls is the average number of customers in the system. So this should be equal to n times pn sum over each possible domain, right? Remember, if you say n is equal to 0, 0 times p naught is still going to give us 0. So that's why we are starting from 1. Okay. So we know what pn is from our previous video. So pn is root to the power n times 1 minus p. Alright. So we substitute this into this equation, and this one is like it's like a Taylor series as function. So you can look at the identity for this, and looking at it clearly, you see that it will give us rho over 1 minus rho. Okay, so which are we know rho is lambda over mu. So substitute that, and you get what lambda over mu minus lambda as our final answer for the average number of customers or elements in the system. So let's look at that of the queue. So remember we said that for the queue length should be equal to what the service length minus the the the, the system length. The system length minus the service length should give us the queue length, right? Because the number of people in the system should be equal to the queue plus the service. And this is a single server. Don't forget, single server. So meaning at all times we are supposed to have one person being served. So the queue length will always be equal to the system length, which is n minus 1, because that's the queue length, right? I hope you understand that. So times pn, that's the probability. Don't forget that. All right, sure. So now we can expand this, and by expanding, we realize that we have n pn minus what pn sum from 1 to infinity. All right, sure. So this one, as we can see, we've seen it. This is the same expression as ls. So we don't need to bother ourselves with this side. All right. So that's ls minus. So let's see this. This like probability of at least one customer in the system, and we know that at least one means one minus no customer. Okay. And when we have no customer, it's like actually p naught. All right. P naught is the probability of having no customer in the system, because we have at least one, meaning that probability summing from 1 to infinity is the same as 1 minus what? None. Alright. So 1 minus none, 1 minus p naught will give us what? Lambda over mu. Okay, and we know ls already. Stop here. So we substitute and we get this answer as our LQ. Okay. Let's look at the average waiting time. So this is the expected waiting time in the queue. Alright. So this can be seen. So usually you see the Poisson and exponential linkages, right? So the average number actually follows Poisson, and the average service time follows exponential, right? Remember the exponential case, the inverse of the Poisson mean is the exponential mean, right? So the same thing is going to happen. So to get the average waiting time, so you just divide it by, you just multiply by the inverse of the exponential mean, and that's going to give us what, or the Poisson mean. That's LQ over lambda, as simple as that. This is the shortest formula you can use for the WQ. Same thing for the WS. So to get WS, all you need is LS. So the formula for LS, you just divide and you get 1 over mu minus lambda. Okay, or you can say LS divided by lambda. All right, yeah. So the expected non-empty queue length, okay, should be equal to mu over mu minus lambda. Take note of this formula. Okay, this is for a system. For the queue will be this. That's 1 over mu minus lambda plus what? Rho. Okay, yeah. So the variance is given by this. So this is the variance. Take note of the variance formula as well. So you take notice. So if we want to know the probability of k having k or more customers in the system, is simply given by rho to the power k. If you want to know the probability of having strictly more than k customers, is rho to the power k plus 1. All right, sure. So the probability that an arrival have to wait in the queue more than w minutes, okay, in the queue is given by rho times e to the power negative mu minus lambda times w minutes. So yeah, and for that of the system is this. So without the rho is not there. Lambda over mu is not there. That makes it for the system, right? Good. So the relationship between these two performance characteristics are seen below. So Ls should be equal to lambda times Ws, or Ws is equal to Ls over lambda, and same thing for here. And Ws, the relationship between the W's two can be seen here. So Ws should be equal to Wq plus 1 over mu, and Ls should be equal to Lq plus lambda over mu, right? So take notice. Alright, so let's solve an example. Telephone users arrive at a booth following a Poisson distribution with an average time of 5 minutes between one arrival and the next. So that should tell you that this is the inter-arrival rate. Alright, this is the inter-arrival rate between one arrival and the next. That's the time, the average time between one arrival and the rest. That's the inter-arrival time. But this is what? This is not the arrival time, but the inter-arrival time. And we know that inter-arrival time is 1 over lambda, right? Meaning 1 over lambda should be equal to 5 minutes. And 5 minutes in hours should be at 5 over 60. Meaning 1 over lambda should be equal to 1 over lambda should be equal to 5 over 60, isn't it? That's okay. So once we do that, we realize that 5 over 60 will give us 1 over 12. And meaning 1 over lambda should be equal to 1 over 12. And lambda should be equal to 12, right? Great. So let's look at the next part. So we say that the time taken for telephone call is on an average 3 minutes. So that how long you're going to stay on the call. That is the inter-service time, right? Inter-service time. So it follows an exponential distribution. The average is 3 minutes. So 3 minutes we convert that 3 over 60 should be equal to 1 over mu. 1 over mu is the inter-service rate. Don't forget. 1 over mu should be equal to 3 over 60, and that will also give us I think 3 over 60 will give us 1 over 20, right? Yeah. So meaning our service rate mu should be equal to 20 as well. So if you want to find the rho should be equal to 12 over 20, and that will give us 0.6. Now I'm coming. Let me move back. So let's see the goal of the question. What is the probability that the system is busy? So system being busy is rho, right? And rho is equal to 1 minus mu. So that will just give us 12 over 20, and that's 0.6. Alright. So how much service rate should be increased in order to reduce the waiting time to less than or equal to half of the present waiting time in the system? So how much waiting time should be increased in order to reduce the waiting time in the system to half of the less than or equal to half of the present waiting time? So let's see, what is the waiting time in the system, right? The waiting time is in the formula. Let's quote it. The formula is 1 over mu minus lambda, so that will give us 1 over 8 hours, right? 1 over 8 hours. So in this case, they said that we should reduce this to, so what is the new service time per customer per hour? Okay, the new one. So meaning we need to equate a new WS formula, which is 1 over mu star minus lambda. So mu star is this service time that has to be increased in order to reduce the waiting time to less than or equal to. These are the equations. So it's an inequality. So we have to take the equality part and solve it. So half of the present waiting time. What is the present waiting time? It's 1 over 8. Half of it will be what? 1 over 8 times 1 over 2. That's 1 over 16. So meaning 1 over 16 should be equal to this equation. We know 12 as our arrival rate. So we solve this equation and we get mu to be 28 per hour. So what it means is that the initial service rate is 20 per hour, and now it's 28, meaning the extra increase in the service rate is going to be what? 8. So hence the increase in service rate should be what? 8 users per hour. Alright? Good. So this is another one. In a self-service store with one cashier, so that one server, 8 customers arrive on average of every 5 minutes, right? So you need to know if 8 customers arrive every 5 minutes, so in an hour time, how many people will arrive? Okay, yeah. So just this question is a trial one. Try for yourself. So 8 customers should be equal to 5 minutes, meaning lambda customers should be equal to 60 minutes in an hour. Then you try to find what lambda is, right? and the cashier can serve 10 customers in 5 minutes. So you need to 10 customers should be equal to 5 minutes. Lamb a meal heavy meal should be equal to 60 minutes. Then you find that one as well. Okay. So they want you to find the average number of customers waiting in the queue. So the answer is this. And the expected waiting time in the queue, the answer is so this. What is the probability of having more than 6 customers in the system? So the answer is so this. So take your time, pause the video and try this for yourself, right? Good. So now, the next challenging thing is that you see, most queues are there, even the world's population is known. We say that the size of the population is infinite. But when we are talking about human beings, sometimes um, we know that the world's population is known, so we cannot have infinite population size, right? So we are trying to say that the system should have what a finite length that is of n, okay, of n. So the system capacity is going to be n customers, so we cannot exceed the n people. And we want to actually derive similar expressions for that case, right? So we are going to use the same thing. So P naught should be equal to P1, P naught plus P1 all the way to Pn should be equal to 1. That is the idea we're still going to use, just like the previous one, right? Yeah. As we do that, you realize that um you realize that this formula, the formula we had before, okay, let's look at this. Let's look at this clearly. I'm coming. I wish I could go back to the performance characteristic equation. This one. Yeah, yeah. So we are in this same equation we are summing up. This same thing. Nothing has changed. But just that we are not summing it to infinity. We are not summing it to infinity. This is the same thing. We are not summing it to infinity. So we are going to have how many customers in the system? Hmm? How many customers? So you see that P naught, P1 to Pn. So you have n plus 1 customers, right? N plus 1 customers. That's why we have 1 minus rho, okay? 1 minus rho. So you have to code the nth sum for a geometric series formula and plug in this common ratio and the common ratio and that of the first term inside, and you end up having this expression, right? Remember P naught to be a constant. All of these P1 can be expressed in terms of P naught, so that is why you have the P naught being pulled out, right? Yeah. So we equate everything to 1, and by making P naught the subject, we have this beautiful equation, right? Yeah. So we can find our LS to be this cumbersome equation over here. Just try to make it a subject. Alright, great. Make LS the subject over there. Also, so let's see an example. So if we assume rho to be 8 over 9, so our P naught will be equal to what? 1 minus this. So you can see that our P naught is given, right? Good. So what will be P1? P1 will be rho P naught. The same thing will happen, just like the single server with the infinite population queue length. The same way. Alright. So that is that. So P naught is P1 is this, okay, and we get our answer as this. So probability of no Q should be equal to P naught plus P1. Let me explain this. So we will have no queue if there's no customer in the system. How will we form a queue? And also one person cannot form a queue, right? So there will be no queue if there's no customer in the system or there's one customer in the system. Because if you are the only person in the system, you don't need to form a queue. Just go to the service straightforward and that's all. There's no need for a queue, right? Great. So probability of 10 people will actually be this, as you know. That's rho to the power n times p naught. Okay? Yeah. So you can actually do a lot of things with this. Okay? Yeah. So let's see a situation whereby we have multiple servers. We've been looking at single server all the time. Let's look at the multiple server view model. So see, you know the number of servers as I've already mentioned. Okay. So the assumption is that um our service rate is not going to be lambda over mu anymore, but it's going to be what? Lambda over what? E times mu. Because the arrival rate you cannot control. But if the number of servers are different, meaning they are more than one, meaning they are going to serve at a rate of what? P lambda. Alright? They're going to serve at a rate of what? P lambda. Okay? And remember the service rate should be less than one. Okay? Yeah, that's okay. So the service rate is always going to be lambda, like just like that, because the arrival rate we have no control over it, but the service rate we can decide the number of servers at our company we are going to employ, right? That's okay. We can decide that. So I saying that this should be equal to n times mu. That is, if the number of customers is less than the the number of servers. Remember, if we have n customers and we have c servers, and this number of customers like are actually in the system, right? It means that all of them will get served because they are even less than the number of servers we have. Otherwise, if we have the n being greater than the c, that means we have more people arriving than the number of servers we have available. That means that we can only the c servers that are available can only serve as their rate c mu, because the first server is going to serve as a rate mu, the second server is going to serve as mu at mu, the next one at mu. So if you sum them c times, that's going to be c mu, right? Good. So if you want to find the Pn, that is the steady state probability, we need to consider both cases, right? So we all know the general formula as this. That's okay. So if n is less than c, okay, n is less than c, then our Pn is to be given as what? Lambda to the power n, because this one is like, remember, root to the power n will give us this. But the mu, the service rate is our challenge. So service rate, the first person is going to be served as a rate mu, serving the second, that's 2 mu, right? And so forth. So we're going to have this to be root to the power. Remember, this one is like n factorial. When we pull the mu out, you can say mu is common here, mu is common there, mu is common here, mu is common. So mu going how many times? N times, right? So that's mu to the power n, and this is lambda to the power n. So they come together. So we just collected the power, the common power. And remember, this is 1 times 2 times 3 times 4 all the way to n. So that's n factorial. There's no confusion here, I guess, right? Sure. So we have to get another one for n greater than or equal to c, and that is beautifully seen over here, right? Yeah. So how do we get our p, not p1 and so forth? So we have to use the same principle. This actually, sorry, this one is actually supposed to be p1, right? We sum everything to 1, and as we do so, you see that we equate it to 1 as well. So what we are doing, we have to sum for all the cases. That means from 0 to c minus 1, because we have to sum this one first, okay? That is n less than c, right? And n greater than or equal to c. If n is greater than or equal to c, then we need to start from what? C to infinity. Do you get that? Yeah. We need to sum both cases, alright, to add up to the 1, because the two cases form the complete probability mass function, alright. So we make p naught the subject from this expression, and we beautifully get it as what you can see over here, right? Don't be scared, you'll be fine. Just take note and take your time to go through these computations. You'll be very fine. Okay? Yeah. Take your time, take your time, take your time. So over here, we've come to the end of Quering theory. Thank you so much for your time being, and God bless you. God bless you.